and sharing the screen. And we left off looking at the area of a circle. Before we get started with where we're going next, does anybody want to look at any homework problems from chapter 10? So far, we've looked at units of measurement, area, and perimeter. Does anybody have questions on any of those? I think those would be the first 2 pages of the homework in chapter 10. Does that mean nobody has questions? If not, I'm going to move on then. And the next thing that we'll look at is the Pythagorean theorem. Have you folks heard of the Pythagorean theorem?
Yes.
What's it say?
I know the formula. That's the
Tell me the formula, hon.
a squared plus b squared equals c squared.
Beautiful. So I think everybody's familiar with the formula a squared plus b squared equals c squared. Oh, you know what? I'm going to shut up for just a second. Quick section. Well, I'm not going to shut up. I'm going to change gears for just a second. Before we look at the Pythagorean theorem, I want to give you a teeny tiny bit of math history. The Pythagorean theorem is named after Pythagoras. I think everybody's heard of him. However, Pythagoras didn't necessarily come up with the Pythagorean theorem. Pythagoras was a philosopher, mathematician in ancient times, and he almost had a cult-like following. He had a school of followers who studied math and philosophy with him. And it's believed historically that Pythagoras himself did not come up with the Pythagorean theorem, but rather his students did. And it's a good possibility that it was even women that were involved in coming up with that theorem. So it was the results of the Pythagorean school, but not necessarily from Mr. Pythagoras himself. So a squared plus b squared equals c squared. I'm guessing that most of you have heard of that. What's c?
Hypotenuse.
The length of the hypotenuse. Oh, and if we're talking about hypotenuse, what type of triangle do I have to have in order to use the Pythagorean theorem?
Right.
So it must be a right triangle. And so if I draw a right triangle, can anybody refresh my memory on what it means for a triangle to be right?
Isn't it equal legs? The legs have to be equal.
The legs don't necessarily have to be equal, but they have to form something.
A 90-degree angle.
Yeah, it has to have that 90-degree or right angle. And so C is the hypotenuse. Help me out here, folks. Which side, if I call this triangle A, B, C, which side is the hypotenuse? AC, CB, or AB?
AB.
AB, beautiful. The hypotenuse is opposite the right angle. And in being so, it's also the longest side. So if C is the hypotenuse, what are A and B?
Legs.
The length of the legs, beautiful. So it's the lengths of the legs. And we can use it a couple of ways. We can use it to show a triangle is right. If the Pythagorean theorem holds true, it's a right triangle. Whoa, I didn't mean to use that pen. To show a triangle right. or to find the missing side of a right triangle. But again, it can only be a right triangle. Common mistake. Sometimes I have students that try to use the Pythagorean theorem for any triangle. And that's not the case. It only works for a right triangle. And so I don't necessarily want to do all of these examples, but let's look at some of these examples that I have further down on the page. Let's look at B. B is a right triangle, so we can use it to find x if I have a squared plus b squared equals c squared. What would you tell me C is? That's the most important one to fill in first because it's the one that specifically must be one of the sides.
17.
Beautiful. And so A and B can be the x and the 8, and it doesn't really matter which you use for which. So I'll say x squared plus 8 squared. So that gives me x squared plus 64 is 17 squared is 170 and 70 is 240. Is that 289? And so
Yes.
when I subtract 64 from both sides, I get x squared is 225. Oh God, now what do I do?
Square root it.
Square root it, beautiful. And the square root of 225 would be
15.
15. Now, next, let's look at F. F is a right triangle, so I can use a squared plus b squared equals c squared. C is 1. A and B are both x. So x squared plus x squared gives me 2x squared equals 1 squared is 1. So here I'd have to divide by 2. And I get x squared equals a half. And x will be the square root of a half. And at this stage of the game, I would rather you leave it as a, because that's not a perfect square, I would rather you leave it like that than change it into a decimal. All right? Some of them are a little bit trickier. If I look at this next one, this standalone problem B, we want to find the length of x. But if I look at x, do you notice that it's a side of that top triangle that is not right? So that does me absolutely no good. But this big outer triangle is right. And I know the hypotenuse, but I don't know either leg all the way. But this bottom triangle is right. And in that bottom triangle, I know the leg and the hypotenuse. So first of all, I'm going to find this side, y. 7 squared plus y squared equals 12 squared. 49 plus y squared equals 144. Now what would you guys do?
Square root the 49 and square root the 144.
Not quite. We want to get that y all alone before we square root. So are you all right if before I square root, I subtract that 49 from both sides?
Yeah.
So that'll give me y squared equals 95. And so y is the square root of 95. Again, 95 is not a perfect square, so back away from the problem. Y is the square root of 95. Now, what I want to do is I want to look at this great big outer triangle. In the great big outer triangle, I'm going to call this leg Z.
Can't you do x plus 7?
You can do x plus 7, but the arithmetic gets uglier if you do x plus 7. Let's do it both ways so you can see what I mean, okay? If I call it Z to start with, I'd have Z squared plus Y squared equals 16 squared, or Z squared plus the square root of 95 squared equals 16 squared, or Z squared plus 95 equals, help, I'm having a brain fart, 16 squared is 256. And so I'm going to subtract 95 from both sides. So Z squared is, did I subtract right there? Is that should be 161, shouldn't it? I apologize. So Z is the square.
155.
This is 256, right?
Yep.
6 minus 5 is 1. 25 minus 9 is 16.
Oh, sorry.
So Z is the square root of 161. And so X would be the square root of 161 minus 7. If I did it the other way, if I took X plus 7 squared plus the square root of 95 squared equals 16 squared, that X plus 7 squared, if you try to multiply that out, you'd get a quadratic. You'd get a, X squared plus 14X plus 49. And I don't think we want to delve into that level of algebra. I guess if you left that as X plus 7 squared plus 95 equals 256, then you could say that X plus 7 squared equals subtracting 161. Then you could say that, I'm going to work sideways, X plus 7 is the square root of 161. And then we'd get that same answer. So I guess as long as you're careful not to take the time to multiply it out, you could have done the X plus 7. They take us to the same place. There aren't many like that in the homework, but that's one of those make you think questions, yes? And you see how we had to use both the little right triangle and the big right triangle. And we couldn't use that tiny top triangle, that standalone triangle, because it is not right. Because that doesn't sound right that it's not right. I'm not saying it's a bad triangle, because it does not contain a 90-degree angle. Does that sound better? I didn't mean to judge the triangle. Oh, well. Is this one okay, folks?
Mm-hmm.
Great. So I don't know. The next one over here, what happens is you have to again solve two triangles. First, you'd have to find X. And in order to find X, we would use this top right triangle. This is 10. This side would be the 15. And so we'd have 10 squared plus 15 squared equals x squared. And then I'm not going to take the time to find the numbers, but I'm going to then look at down here at the bottom, this right triangle. Then I'd have that 7 squared plus x squared equals y squared. So that one's a little bit different. You kind of have to picture the two right triangles in there. The cone, I think, is pretty straightforward. Does everybody see to solve the cone? We would have x squared plus 12 squared equals 13 squared. And once it's set up, is everybody okay with finishing it?
Would it be wrong if you did x squared plus 13x squared?
Yes. When we're looking at a squared plus b squared equals c squared, a and b have to be the legs. C has to be the hypotenuse. All right?
Okay.
This next one, I think I put in the homework, but I thought I might try to help you folks a little bit with it. If I look at this one, a squared plus b squared equals c squared. The legs are r and 24. And ew, this time the hypotenuse is r plus 18 squared. And this time, there's no way of getting around that r plus 18 squared. So r plus 18 squared is r plus 18 times r plus 18. And having successfully completed an algebra class is a prerequisite for this class. And this is one of the reasons why. Does everybody remember when I multiply two terms by two terms, you can either use a box, or you can distribute twice, or you can FOIL. I'm a FOILer. So first, r times r is r squared. Outer r times 18 is 18r. Inner r times 18 is 18r. Last 18 times 18, oh my heavens, 18 times 18 is 6, 144, and 180 is 324. So we get r squared plus 24 squared is equal to r squared plus 36 plus 324. And what makes, I'm sorry, that should be not 36. I apologize. That should be 36r. But now do you see I can subtract the r squared from both sides? And so I get 24 squared. And I have to apologize. I need to multiply that times out. 1696, 48, 6. So we get 570. 576 is equal to 36r plus 324. And then from there, it's not too bad to solve. So I'm going to stop there. But does that process, taking this and multiplying it by itself to get this expression, does that look vaguely familiar? Everybody all right if I stop there and leave the rest for you to finish? Because I know
You would just divide the 36 into the 252, right?
after you subtract, yes, ma'am.
Okay.
Okay. Then the converse again, that's saying that if a squared plus b squared equals c squared, it must be a right triangle. And that's that idea of testing to see if you have a right triangle or not. And that gets me to something that's called Pythagorean triples. If you notice, going back a little bit, preceding page, when we used the Pythagorean theorem. Some of them gave us whole numbers, but a lot of them didn't give us whole numbers. You can get into radicals very quickly with the Pythagorean theorem if you just use any two numbers for the sides that you know. If you want to make sure that you get whole numbers, what happened to my page? Yikes, where were we? If you want to make sure that you get whole numbers, you want to use Pythagorean triples. They're whole numbers that satisfy a squared plus b squared equals c squared. And so one that's commonly used is the 3, 4, 5 right triangle. And we can say that 3 squared plus 4 squared equals 5 squared. 9 plus 16 would be 25 equals 25, and it checks. But what's cool with these triples is it's not just those numbers, but it's also their multiples. So what do I mean by multiples? If I look at that 3, 4, 5, if I multiply by 3, for example, I would have 9, 12, 15. Is everybody all right? I just tripled all of those numbers.
Mm-hmm.
And if I look, 9 squared plus 12 squared should equal 15 squared. 81 plus 144 will give me that 225. And so if you're trying to come up with a sheet of practice for children using the Pythagorean theorem, and you don't want them to have to mess with radicals, 3, 4, 5, 5, 12, 13, 7, 24, 25, some of them, your numbers start getting a little bit bigger, but using those triples and their multiples makes life easier. So I just look at a couple of them, but this morning I was thinking and I scrolled through and found this table of Pythagorean triples that I thought might be useful to you if you are ever teaching the Pythagorean theorem and you don't want the kids to have to bang their heads against the wall with radicals. Okay? Pythagorean theorem, all right.
Yes.
Yes.
Then next page, I think the next two sections of the book deal with surface area and volume. And we're going to first look at volume. And the volume is like the space inside a solid. The surface area is like the sum of the areas of all the faces. Back in the day, when I used to teach this course a couple of times every semester, we used to have a lot more students in the education program, a lot more students taking this course. It wasn't unusual to have many sections of this during the day. And in talking about the difference between surface area and volume, I likened it to that big December holiday, which, where people are constantly looking at the idea of gifts. And I thought of the volume as being how much the box holds on the inside, and the surface area, being like how much gift wrap you need to cover the outside. Does that analogy make sense for everybody? And so if I look at a rectangular prism, we say that the volume is equal to the length times the width times the height. And so if I look at this blue rectangular prism, I could call this side the length, this side the width, and this dimension here the height. And what I'd like to do, rather than focusing on a specific formula for each prism, I want to generalize to all prisms, no matter what the shape the bases are. And so over here, if I look at just this part, the length times the width, wouldn't the length times the width be the area of the base? And so if I have any prism, and this will also hold true for a cylinder, I'm going to look at the volume as equaling uppercase B times H, where B is the area of the base. And so let's, I'm going to scroll down to the blank space at the bottom of the page and look at two examples. First, let's look at a right triangle, triangular prism. And so the bases are going to be right triangles. And so let's say in each of these right triangles, the length of this side is 3. Let's say the length of this side is 4. And let's say that the height is 6. The volume, because it's a prism, it's going to be the area of the base times the height. And so if B is the area of the base, I'd need the area of a triangle, which is 1/2 base times height in the triangle. And again, in a triangle, the base and height have to be perpendicular. They have to meet at that right angle. So that would be 1/2 of 3 times 4. So let's see, 3 times 4 is 12, half of 12 is 6. So the area of that base is 6 square units. And so the volume would be those 6 square units times the height is also 6. So that would be 36. And when I take the square units and multiply it by the units, I'll get cubic units. And so when I'm looking at volume, volume is measured in cubic units. It's like, how many little boxes can I fit inside of there? Instead, if I have a cylinder, the top and bottom are circles. And so let's say that our cylinder has a radius of 7 inches and a height of 10 inches. The volume, because the two bases are the same in parallel planes, the volume is the area of the base times the height. The B, uppercase B is the area of the base, which for a circle is pi r squared. So that would be pi times 7 inches squared would give me 49 pi square inches. And so the volume would be that number, that 49 pi square inches, times the height is 10 inches. And so 49 times 10 would be 490. I'm going to leave it in terms of pi. And then square inches times plain old inches would give me cubic inches. And you see how if I've got something like a prism or a cylinder where I've got two bases that are congruent in parallel planes, I just need to get the volume to find the area of that base and multiply it times the height. Are we good? Okay. Now I'd like to try to show you something. I don't know how well this is going to work, but I'm going to give it my best attempt. That was why I was fighting that echo. If you just give me a second. This is that, I believe it's activity 9 that I had said that we would try to work together in class on. And if we were on campus, I would hand out to everybody a set of relational solids, and I would, I would be giving you all in pairs a set of relational solids and of all things a pound of salt, and ask you to do the following. So I'm going to stop sharing, and I'm going to try to place the computer on a stand in such a way that the camera is through a hole in the stand. And I want to compare the volume of a prism. Can everybody see my triangular prism?
Mm-hmm.
Is it clear enough? I want to compare that to the volume of a pyramid. And can everybody see my triangular pyramid?
Yes.
I'm going to compare them. If I put a sheet of paper or something across the top, we would see that they have the same height. And if I pop the base out of my pyramid, do you see how they have the same bases? So
Yes.
on its two shapes, the bases are equal. Let me pop this base out. They're congruent, and the two shapes have the same height. I want to compare the volume of my pyramid, how much stuff I can fit inside of it, to the volume of my prism that has the two bases that are parallel. We know the volume of the prism is equal to the area of the base times the height. In order to compare them, is everybody all right? By inspection, the pyramid looks like it would be a much smaller volume than the prism. It fits inside it with room to spare. So what I'm going to do, with hopefully not making a mess on my dining room table, is I'm going to fill the pyramid. I use salt. The relational solids had come with these little BBs, but they're too big. I had thought about using sand, but then I thought when I was doing this in a classroom, that sand would be a mess all over the floor. And I was grocery shopping and realized that you could get 3 of those containers of salt for $1. They were on sale, really cheap. And I thought, well, if salt goes on the floor, it dissolves when they clean the floor. So I figured that was the least messy thing to do. And so do you see how that's way much, the volume of the pyramid is smaller than that of the prism?
Mm-hmm.
So let's see. Let's fill it again. And again, I'm filling it to this, there's a line there where the base would attach. And wow, 2 weren't enough, were they? Let me try again. Can you guys see okay? I had wanted to have that other computer up so that I could see what you were seeing, and I can't see what you're seeing. Is this clear enough to you guys?
Yeah.
And when I pour this in, wow, do you see how 3 fill it perfectly? So it takes 3 pyramids to fill the prism when I'm looking at the triangles. Let's try another shape. For my other shape, I'm going to go all crazy. And can everybody see the cylinder and the cone? Can you see them or no?
Mm-hmm.
So let's pop the bases out. They have the same height. Notice the bases are the same. How many cones do you think it will take to fill the cylinder? Any ideas? Any guesses? How many of these do you think it'll take to fill that?
1.
Oh, 1 went in and it didn't fill it, did it?
No. I
Let's
thought you were
try-
talking about the green cup. That's why I said 1.
No. How many of these cones do you think it's going to take to fill this cylinder? 2 didn't do it. Let's try one more. Well, it's not exact, but do you see how 3 would fill it? And so notice that if the pyramid and the prism have the same base and the same height, it takes 3 pyramids to fill the prism. If the cone and the cylinder have the same base and the same height, it takes 3 cones to fill the cylinder. And if we were on campus, you would be doing this on your own, which is what the activity is asking you to do. And we would then also do it with the cube and the square pyramid. And would you believe me if I said it takes 3 pyramids to fill the prism? So hopefully from that display, although if we were on campus, you would be playing with the salt and the shapes on your own. Hopefully from that hands-on display, we can justify the idea that if I have a pyramid or a cone, the volume is 1/3 that of the prism or cylinder, so that the volume is 1/3 the base times the height. And that fraction 1/3 comes from that idea that it takes 3 of one to fill the other. So let's say, for example, I have a square pyramid. the base is, let's say 9 centimeters by 9 centimeters. And the height is, let's say 10 centimeters. Because it's a pyramid, because it comes to a point, the volume for a prism, it would be base times height. But if it comes to a point, we'll take 1/3 of that. Remember, B is the area of the base, which for a square would be length times width. 9 times 9 is 81 square centimeters. So the volume would be 1/3 of that 81 square centimeters times the height, which is 10 centimeters. I put an extra C in there, didn't I? 1/3 of 81 is 27. So 27 centimeters, pardon me, times 10 centimeters will leave me with 270 cubic centimeters. All right. And I hope that showing you that it takes 3 of these to fill 1 of these helps you remember why that 1/3 is there. Okay? Then if I have a sphere, if I have a ball, just an aside, making note of the fact that the volume is 4/3 pi r cubed. When I teach the calculus class, we go through and derive that formula. We're not going to do that in this class. We're just going to make note of the fact that the volume of a sphere can be found by 4/3 pi r cubed. I promise I will not throw that one on the test, just making note of that fact. And again, volume is in cubic units, so it makes sense that I need to raise that to the 3rd power. Volume formula is all right. Then, next thing that we look at is the idea of the surface area. We're looking at the surface area of a right prism or a cylinder. And if you wanted to, you could find the area of all the faces and add. Or we can use this generalized formula. The surface area is 2 times B plus pH, where uppercase B is the area of the base. P is the perimeter of the base. And H is the height of the solid. And if I take, for example, this rectangular prism, if I were to look at its net, if this is the base, I'd have 2 bases. That would be these 2 sides, the top and bottom. And then if I were to take it apart, wouldn't those lateral sides form one great big rectangle? And when I look at that great big rectangle, wouldn't this side of the rectangle, wouldn't the length of that side be the perimeter of the base? Because when I put that box back together, it goes all the way around. So I'm going to draw a better arrow here so that the length of that great big long side here would be the perimeter of the base. And this would be the height of the prism. And so I'd take the area of the base and I'd have to double it because I have two bases. And then I'll take the perimeter of the base and multiply it by the height. Instead, if I were to dissect that cylinder, think of taking a can apart. I'd have the top and bottom. Those would be my bases. And then wouldn't I have a great big long rectangle where one side of the rectangle would be like the circumference of the circle. So let's use a cylinder for the example. Let's say on my cylinder, the base has a radius of 2, and the cylinder has a height of, oh, let's make it 5. Its surface area is twice the area of the base plus the perimeter of the base times the height. B, the area of the base would be the area of the circle, which is pi r squared, or 4 pi. P would be, the perimeter would be the circumference of the circle, which is pi times the diameter, which is 4 pi. So my surface area is 2 times the base, 4 pi, plus the perimeter, 4 pi, times the height, which was 5. So that would give me 8 pi plus 20 pi, or 28 pi square units. Again, because surface area is area, we measure it in square units. And I'm looking at the clock, and I wanted to get to the surface area of a pyramid, and I did not yet. And so we will pick up there on Monday after we look at those surface areas, if you humor me for a minute. We just have to look at the ratio between length, area, and volume. So we should be tying up this chapter on Monday. And so having that homework due on Friday seems just right. Wednesday, we'll tie up loose ends if anybody wants to look at any of the homework problems or the activities. And then next weekend, you'll have that test on chapter 10. Any questions on anything? I'm thinking, Emily, I let you in?
Yeah, I was having a conference with my teacher and I ran over time a little bit.
That's okay. I just want to make sure I got that you were here. And because I was a total failure at being in the Zoom meeting on 2 machines at the same time, because again, I wanted to be able to watch the demonstration on the other computer so I could move things if I had to, because I had no idea what it looked like for you guys. Did it look okay, demonstrating like that? Was it clear enough?
Mm-hmm.
Okay, so if I use something like that when we do constructions and do some of the drawing, if I do it that way so you can actually see my hands and my compass as opposed to just what I write on the screen, that'll work?
Mm-hmm.
Okay, because that's that hands-on part is what I'm worried about with this class being virtual. Did anybody else come in after I took attendance? If not, have a great weekend. I'm sorry I ran 2 minutes over. If you have any questions, please shoot me an email. Bye-bye.
Bye, have a good weekend.
You too.
Thank you.
Cameron, Marie, and Elizabeth, are you two all right? Are you there? I'm going to end the meeting. Bye-bye.